All right, today we're going to dive into a really cool AI concept. It sounds a bit complicated, temporal difference prediction, or TD prediction, but trust me, the idea behind it is actually super intuitive. It's one of those things that once you get it, it just clicks.
So let's start with a puzzle. How in the world can an AI, say playing a game of chess or Go, have any idea who's going to win right after the very first move? I mean, think about that. It's seen almost nothing, yet it has to make a prediction about the entire future of the game. That's the huge challenge we're talking about today. How do you make smart, long-term guesses with barely any information to go on?
To really wrap our heads around how this works, let's just push all the AI stuff to the side for a minute. We're going to use a super simple analogy, something we've all experienced: the daily commute. Okay, so picture it. You're leaving work. You've done this drive 1,000 times. You glance at the clock and you just kind of know. You make a quick guess in your head, right? Yeah, should be about 30 minutes to get home. That's your first prediction based on all your past experience.
So you hop in the car, put on some music, and for the first 10 minutes, everything's going smoothly. But then you round a bend and bam, a sea of red brake lights, a total standstill, an unexpected massive traffic jam. Suddenly, you have a new piece of information and it completely changes the game.
Now, here's the key question. Do you need to wait all the way until you pull into your driveway to figure out that your 30-minute guess was way off? Of course not. You know it right now. Sitting in that traffic, you immediately know your initial estimate is toast. Waiting until the very end to update your thinking would be, well, kind of pointless and super inefficient. And that right there is the exact problem that TD prediction solves. So, before we get to the really clever solution, let's take a quick look at a couple of the older ways people tried to solve this prediction problem. We'll call them the classic solutions, and you'll see pretty quickly why they both have some major flaws. First, you've got what we can call the patient method, technically known as Monte Carlo. The rule here is super simple. You wait. You wait until the entire journey, the whole episode, is over. Only then do you look back and learn. So in our commute analogy, this means you drive all the way home, get stuck in traffic, finally walk in your front door, look at the clock, and then you say, that wasn't 30 minutes, it was 50. You only update your belief after you have the final true answer. It works, but man, is it slow to learn. Okay, on the complete opposite side, you have the know-it-all method, or dynamic programming. This approach is way faster. It can update its predictions at every single step. But, and this is a huge but, it needs to have a perfect map of the entire world. For our commute, this would be like having a godlike GPS that knows where every single car is, where they're going, what every traffic light is about to do. It knows every possible thing that could happen in advance. I mean, sounds amazing, right? But it's totally unrealistic for just about any real-world problem you can think of. So what do we have? One method is way too patient, and the other one needs to be psychic. Not great options, right? This is where our hero comes in, temporal difference learning, or TD. It's this beautiful hybrid that takes the best parts of both of those other methods and ditches the bad stuff. So what's its first superpower? Well, compared to that super patient Monte Carlo method, the big advantage is you don't have to wait anymore. Monte Carlo waits till the very end of the trip. TD, on the other hand, updates its predictions as it goes. It learns on the fly. And its second superpower? When you put it up against the know-it-all method, dynamic programming. TD doesn't need that perfect magical map of the world. It doesn't need the psychic GPS. It learns directly from experience, from the journey itself, just like you when your own two eyes see that traffic jam up ahead. Okay, so this sounds kind of like magic, right? Learning on the go, but without a perfect map. How does it pull that off? The answer is so simple and so powerful, it's brilliant. It works by learning a guess from another guess. This amazing little trick, this secret sauce, actually has a name. In the world of reinforcement learning, we call it bootstrapping. And don't let the fancy names scare you. Bootstrapping is just what it says here. It's when you update your current guess based on one of your future guesses. You're not waiting for the final 100% correct answer. You're just learning a guess from a guess. That's really all there is to it. Let's just walk through this one more time with our commute, step by step. So, Step 1, I'm leaving the office, and my first guess is 30 minutes. Easy enough. Step 2, now I'm 10 minutes into the drive, and I see the traffic. I look at the mess ahead, and I make a new guess, a more informed one. I think, okay, from right here, it's probably going to take me another 35 minutes. Now step 3, and this is the bootstrapping magic. I immediately update my original thought. I take the 10 minutes I've already spent driving, and I add my new guess of 35 minutes. And boom, I now believe this is a 45-minute commute. See what happened? I updated my guess about the start of the trip using a new guess I made from the middle of the trip.
And really, this isn't just our little analogy. This is the core of it. There's this great quote from the book that literally wrote the book on reinforcement learning, and it says it all perfectly. TD methods update their estimates based in part on other estimates. They learn a guess from a guess. It's as simple and as powerful as that.
All right, so let's boil this all down. If you walk away from this with just one single idea in your head, what should that be?
Here it is. TD learning is all about making smarter predictions by constantly updating your beliefs on the fly, using your own new and improved guesses. It doesn't wait for the final answer. It learns step by step from its own journey. And that's what lets an AI learn and adapt in a complex world, one moment at a time. It really makes you wonder, right? If an AI can get this good at learning from its own guesses, how long until its guesses become even better than ours?